aware. So, welcome to everyone, and good morning to everyone in Europe, and good afternoon to everyone in Asia. I'm happy to see that so many could join today. This is kind of the first webinar that we're hosting that is especially dedicated to our academic collaboration, which we in the OPTOCE project launched about a year ago now. In this academic collaboration, we have partnered up with different research institutions in our partner countries. And today we will hear from them and we will learn some more about the research that they are conducting. And most of the studies, they are not finalized yet. So as you may have noticed, we're calling this a progress report. So we're showing the results up to now. And we're planning to host another meeting or a webinar at a later point to discuss the final results. And before we formally begin, I would like to encourage everyone, all the audience, to ask questions or comments in the chat, which you can find when you click below, to the presenters. We have set up time for a questions and answer session after all the presentations. So I hope we get some interesting questions from the audience. And that also means that we will not do a question session after each presenter, as we set up time for that later. And also all the presentations will be sent to the audience after the webinar. So you can look through them then if there's something interesting. And finally, I would like to ask everyone who is not presenting to stay muted during the webinar, which it seems like you all have under control. So. Yeah, so with that being said, I now have the honor of welcoming the woman who will give our opening remarks of this webinar. As you might have seen in the agenda, it was supposed to be Mr. Stig Tråvik from NORAD who was giving the opening remarks, but he is unable to join today. But luckily we are in good hands as Lauren Nabil Gisnos from NORAD was able to join. Lauren has been a part of our project since the very beginning. She's a senior advisor at NORAD, the Norwegian Agency for Development Cooperation, who is funding the OPTOCE project. So she knows the project pretty well, and we're very happy that you could join us. And please, the floor is yours, Lauren.
Thank you very much, Anneli, and it's really a pleasure for me to be here. And hello to the SINTEF team in Norway and also to your partners in Thailand, India, China, Myanmar, and Vietnam, or good afternoon to you in Asia. So it's really an honor to be here to open the first the seminar on the first progress report from the academic collaboration under the SINTEF OPTOCE project. So first, some facts. We like to talk about facts at NORAD. So the world today is only 8.6% circular. This is according to the Circular Economy Gap report from this year. This means that more than 90% of the resources that we are using are not going back to circulation. And plastic production has increased by 9% every year since 1950. So in total, 8.3 billion tons of plastic has been produced until now. And this is dominated by single-use plastic, such as packaging. And much of this plastic waste is non-recyclable. And less than 10% of all plastic used has been recycled. So there's a huge amount of plastic used, and the fact that more than 2 billion people lack access to safe waste management has resulted in our crisis of ocean pollution. And this is affecting marine wildlife, biodiversity, ecosystems, and people's lives, of course. So people and communities who depend on ocean resources for job, food, and income and tourism are being affected by this plastic pollution. So in 2018, the Norwegian government initiated the development program to combat marine litter. This development program is aimed to contribute to SDG, so the Sustainable Development Goal 14.1, which is to prevent and significantly reduce marine pollution of all kinds by 2025. And the OPTOCE project is supported by this marine litter program from the Norwegian government and will be a solid contribution to the achievements of the program. And the program will run until 2024, the development program. The OPTOCE project is unique as it focuses on treatment options for non-recyclable plastic waste in partnership with industry. And working upstream is of course important, but we can't wait for the system changes upstream. There are already enormous amounts of waste in nature that need to be treated. Piloting the use of non-recyclable plastic waste as fuel in cement production is a real innovation in circular economy. It can reduce coal consumption and create treatment capacity for plastic waste. So it's also a solution for the climate issue. The project is ambitious and it encourages for local solutions to a global crisis. The academic collaboration is a strong addition to the OPTOCE project. More research and increased knowledge on non-recyclable plastic waste locally will support science-based policy and decision-making. This is through excellent partner universities in Thailand, India, China, Vietnam, and possibly Myanmar as well. This is also a platform for sharing lessons learned and create synergy between countries, which is really important. NORAD is a proud supporter of the OPTOCE project, and as Anneli mentioned, I've been following the project since the start. I'm now happy to open this webinar where you will share progress and build competence on treatment options for non-recyclable plastic waste. Thank you very much for your attention, and I wish you a successful webinar. Over to you, Anneli.
Thank you so much, Doreen. Inspiring words and interesting facts. I think it really helps to kind of set the scene and remind us that the work we're doing is important and matters. So that's good. Thank you. And I hope you get the chance to stay throughout the webinar and listen to our interesting presentations. Okay, so next up is the man who is leading it all, the program manager of the OPTOCE project and chief scientist at SINTEF, Dr. Kåre Helge Carstensen. Dr. Carstensen initiated the OPTOCE project in late 2018, and he has since then been leading us with a steady hand. And today he will introduce the project and our progress so far. So, Kåre Helge, up you are, and you're muted. You're still muted.
Yes, now can you see it?
Yes,
Yes.
we can see, not presentation mode yet, but.
You cannot see the presentation?
Yeah, we see the presentation, but it's not in presentation mode. We see all the slides.
Let me just, okay, you know this, it's blocking. It's blocking my, just a moment. There it is. I had to remove it. Okay, sorry for that, but I think we have some time. Good morning, everyone. It's really nice to see you, and it's really nice to see the interest and so many participants. That's very good, despite the fact that we have been sitting more or less in home office for the last 15 months. At least we have in Norway. I would say that I feel very optimistic these days. We just heard, we had a small chat with some of the professors already, and they have got their jabs or will have their jabs very soon. And I think that's very encouraging. We see signs of opening up here in Norway, and we, the OPTOCE team and SINTEF is really looking forward to come back into action and to continue our work with you in the field. So let me just remind you a little bit by giving this brief presentation about the whereabouts and the aim of the OPTOCE. And as Miss Loreen actually mentioned, the Norwegian Development Program actually was launched in 2018 and had a few focus and outcomes. Actually, management of plastic waste in part of the country is improved, should be improved. Selected coastal areas and rivers are cleared of waste, and the waste is sustainable managed. Private sector performance regarding sustainable production and use and responsible waste management is also improved. And global commitments and national and regional instruments to prevent marine littering are strengthened. So these are the main objectives and the outcome of the entire program. And I think if you remember these 4 points, you will see that OPTOCE seems to be in alignment of these objectives. But just continue where Laureen actually left in her presentation, namely about plastic and plastic waste. Plastic has been produced since the 1950s in huge amount. We reckon that more than 9 billion tons of plastic has been made, and more than any other manufacturing material. And the reason is numerous, of course, but we have to remind ourselves that plastic is based on fossil oil or polymer hydrocarbons, often with some additives. It is possible to shape in various forms, like bottles, for example, spoons, forks, etc. It's moldable if you heat it. It's also very durable and strong and robust, which is a very, good feature of such tools. But it has some potential drawbacks, and that is that it doesn't degrade easily. If you leave this plastic or plastic waste in the nature, it will break down physically to microplastic over time. It doesn't mean that it will disappear, but it will break down to smaller pieces, which, for example, fish and marine life may think is food or something else. So that creates a possible challenge for us. Of course, we would like to see that all the plastic produced is actually recycled, but unfortunately, as we also heard Laureen mention, less than 10% has been recycled up to now. And the reason is that recyclability depends on various aspects, which I will come a little bit back to. But for example, the polymer group. As you can see on the right, where the PET bottles is at the screen, you will see that it has number 1. And all the plastics that we produce today is numbered from 1 to 7. And only 2 of these plastic categories is readily recycled. The 5 others are very often not recycled or dumped. But the plastic waste has another feature which might be usable, and that is that it's high in energy content. So let's see if we can combine these characteristics into some solution-based options. There is no doubt that insufficient waste management infrastructure in developing countries and emerging economies. But not only those, we also have problems in Europe and elsewhere. But anyway, especially connected to major world river basins, landfills, and industrial sites, seems to be a challenge when it comes to management and treatment of plastic waste. And if you look at the picture on the right side, you will see the durability or the length before some of these items are decomposed. And for example, if you look on a PET bottle on the lower right, you will see that it will hardly be decomposed, maybe ever, depending on where it ends. If it sinks down in the biggest deep outside Japan at 11,000 meters with very less oxygen, very few bacteria, etc., it will probably stay there forever. And that is a problem if the sea floor is filled up with plastic waste. We reckon that around 8 to 13 million tons of plastic leak into the oceans every year. I think these figures are probably a little bit underestimated, and I think research in the near future will show that this is the case. But anyway, there is no doubt that if we don't do anything with the plastic soup that we now see in 4 or 5 major areas in the big oceans, then we will actually have more plastic than fish in the ocean by as soon as 2050 or even earlier. And microplastic is, of course, of no benefit to any. It might harm the biodiversity, the economy, and of course, potentially our own health. So we are actually dealing with a big experiment, which is unique today. Out of the more than 9 billion tons produced of plastic, around 6.3 billion tons has ended up being plastic waste globally. And around 9% has been recycled. Around 12% has been incinerated in various forms of incineration, but very common today is to use waste to energy incinerators producing electricity. While almost 80% has been dumped, meaning that we can find plastic waste actually everywhere. And we facing today probably more than 5 billion tons of plastic waste in dump sites, as you can see on this photo. This photo is taken in the Mekong area in the south of Vietnam. And they try to cover it with some sheets and some cover up, but of course that will not prevent it to degrade and end into the river. It will slowly break down and be released sooner or later into groundwater, river, etc., and probably constitute a continuous source of microplastic to our oceans. And if you look to the figures I just mentioned, to the 8 to 13 million tons released to this ocean every year, I think these releases from groundwaters, from rivers, etc., in the form of microplastic or smaller plastic pieces is not into the bigger calculation. So that is a concern, of course. The objective of OPTOCE is actually to investigate how the involvement of resource and energy intensive industry like cement manufacturing. We can also look into steel production, into coal-fired power plants, etc. But as of now, we are concentrating on cement production and how this involvement can increase the treatment capacity for non-recyclable plastic waste in China, India, Myanmar, Thailand, and Vietnam. And please remember, this project is only focusing on non-recyclable plastic waste treatment. The OPTOCE countries is, of course, a super important region in many ways. They have a population of around 3 billion people. Many live along coastal areas. They are among the highest plastic consumers in the world, with some of the highest releases to the ocean, and generate an estimated 176,000 ton plastic waste every day. It's an astonishing number. And in common, they all have insufficient waste management infrastructure and treatment capacity. So anything is welcome if we can show that, for example, our option is feasible. Because on the other side, they also represent, an industrial region. They produce more than 75% of the world's cement, steel, and electric power in tens of thousands of plants, using huge amount of coal, and contribute with a large chunk of the world's CO2 emissions. Replacing parts of the coal with non-recyclable plastic waste seems to constitute a win-win opportunity. And this is often called co-processing or integrated waste management, and is common around the world, especially in Europe, in the US, etc. If you look to our main challenge today, namely global warming and CO2 emissions, we saw that the CO2 emissions were continuing to rise in 2019. China was accounting to 28%, India 7%, The latest figures for 2020 is not out yet, but we have seen a dip in the CO2 emissions in some of the countries. China is probably one of the few countries which really didn't dip in 2020, it seems. But anyway, I think what we see today is that everyone is back on track on increasing their emissions, and we need to do something with the CO2 emissions. I will skip these slides. So what is the opportunity of replacing coal with plastic waste? On the upper orange line, you will see plastic polyethylene is mentioned, and it's given the value for the net calorific value or the energy content. And you see it constitutes around 46 megajoule per kilo, while bituminous oil is at 27, meaning that plastic actually has 70% more energy than coal. So that might create an opportunity, of course. Especially when you look to cement kilns, they use huge amount of coal. And here you see a kiln in China. And this is, here I'm putting up the benefits of using cement kilns. Basically, they are already in place and in operation 24/7. So you don't need to build an incinerator or a new landfill. They have a large waste treatment capacity. Some of these kilns can take 20, 30, 40, 50 tons waste every hour. And they have a very high energy recovery efficiency, for example, compared to incinerators. We are talking about significantly higher energy efficiency. It's a complete and final disposal solution, for example, compared to incinerators, which produce a lot of residues and ash and flue gas treatment residues, which needs to be landfilled. This is not the case in a cement co-processing scenario. Everything is taken care of. It's a closed and final disposal solution. It, of course, reduces the coal and the raw material consumption, basically because the ash in the plastic will be also part of the product. Emissions will normally be unaffected if this is done in a proper and responsible way, and it reduces CO2 compared to building incinerators or landfills, of course. And it's usually very cost efficient compared to building new incinerators or new landfills. We see that more and more in Europe, that the cement industry is actually competing very well with the incinerator business. They also have some other features which is beneficial. They have very high temperatures, long residence time, and surplus oxygen, which will actually ensure that if you have any contaminants or any organic hazardous constituents or chemicals, it will be totally destroyed if this is taken into a cement kiln. And that's also a beneficial feature compared to incinerators. And this feature has been using beneficially in Norway for the last more than 30 years. We have only been using our cement industry and our cement kilns to destroy, for example, our organic hazardous waste. So we never built a dedicated incinerator to destroy the organic hazardous waste. We are only using the cement industry, which is today taking a whole range of other waste streams, of course, and they have a TSR, thermal substitution rate, of more than 75%, meaning that they can actually replace more than 75% of its coal with various waste streams. So this is beneficial both from the society point of view. We didn't need to build a very expensive and dedicated incinerator. We avoided an additional emission source. The cement industry became more competitive and they can save resources. And of course, the country reduces its CO2 emissions. If you look to Asia, you will see that co-processing in the cement industry is lagging a little bit behind. We reckon today that the average TSR, thermal substitution rate, is around 3%, meaning that they replace around 3% of its coal. So this creates, of course, an enormous potential for co-processing and to increase waste treatment capacity, to save resources, energy, and to reduce CO2 compared to building incinerators or landfilling. I will give you just a few, other points, which is now very into the focus, and that's the new European Green Deal. they have really, really ambitious targets of, reforming industry production, introducing circular economy, reducing plastic waste, etc., which is all of these aspects, most of these aspects in the European Green Deal fits very well into the objective of what we are doing in OPTOCE. And the same with the new EIA roadmap, which is called Net Zero by 2050 for the global energy sector, which really wants to actually reform the energy sector by introducing solar and wind, but also using circular economy and resource efficiency and co-processing. This is a very vital part of this roadmap. And I will just read the last part. This pathway requires vast amounts of investments, innovation, skillful policy design, and implementation, technology deployment, infrastructure building, international cooperation, and efforts across many other areas. So I think this was launched in May a few weeks ago and has created a lot of attention around the world. And when we are now moving towards the Glasgow meeting in November, December, which will continue on the path for the Paris Agreement and to try to keep the world on 1.5 degrees centigrade, I think co-processing and the tools that we are using might fit very well into this context. We want to showcase that it's possible to use local industry. We want to test and document the performance, basically describe the circularity, plastic waste co-processing capacity, environmental performance, cost and energy efficiency, need for pre-treatment, limitations, etc. And to come up with a quantitative and qualitative assessment how the involvement of private industry can actually improve plastic waste management and prevent marine littering in each country. This is a map of the 5 OPTOCE countries. Now I will just very briefly mention what we are doing in these 5 countries. But just to start, these are the 4 main streams of non-recyclable plastic waste, which we are currently dealing with. That is plastic from dump sites and landfills, which cannot be recycled. It's plastic from big rivers, which cannot be recycled. It's plastic from larger industry, for example, paper recycling in Asia, which produce large amount of plastic waste, which is not recyclable. And it's also non-recyclable plastic waste generated from recycling companies in big cities and municipalities. I will very, very quickly go through what we do in these countries. I will not even mention what we do because this will be reflected in the next presentations. But just to mention to you, in China, they produce close to 50 million ton plastic waste. And we have a few pilots ongoing. We actually did a pilot in Yangtze River, which we will hear more about soon, I think. In December, where a huge amount of floating material was collected and used in an upstream cement plant in Sigui. And we are actually evaluating the data from these pilots in these days. India, close to 10 million ton. We have had a small setback in India because some of the bigger pilots that we were discussing with the Ministry of Environment and Forest in India has been in a way delayed or even might not happen. So we are discussing with other companies these days actually to come up with some good alternatives in India. We are dealing with Goa Waste Management in Goa and we are looking for some other alternatives. Thailand, more than 3 million ton plastic waste. We have a few pilots going on. One is dump site mining together with INSEE, the second largest cement producer in Thailand. And we have also a research activity with AIT outside of Bangkok. In Vietnam, they produce close to 3 million ton plastic waste. And we have a few pilots. One is with the biggest paper recycling plant in Can Tho and Mekong River Delta. and the other one is a cooperation with UNDP project in collecting and using the non-recyclable plastic waste as a co-fuel in cement industry. In Myanmar, as you probably know, we have the unfortunate situation with the coup in Myanmar, so everything is a little bit on hold in Myanmar. But we were working with the World Bank, the Asian Development Bank, to produce plastic management action plans and to provide technical assistance to the government. But as mentioned, this is on hold for the time being. We have a few other partners which are keen to work with us. And of course, apart from reducing marine debris, we also want to enhance multi-stakeholder coordination and partnerships. We want to promote private sector engagement. I think this is very, very important. We have been working on this issue more than 30 years around the world, and we always see that if we involve private sector, something will happen. If we only deal with governments, unfortunately, many things will actually be staying in the office. So we need to create a platform for collaboration, and the sector and industry is very important in this aspect. And also research. We see that there is a lack of science-based research for policy and decision making. And I think this is one of the aim and goal of our collaboration with our academic partners. We actually want to build know-how on the fate of plastics in dump sites and on treatment options for non-recyclable plastic waste. We want to collect knowledge about the situation for non-recyclable plastic waste in each country, and we are funding research and Master of Science and PhD thesis projects in these countries to support the objective and the aim of OPTOCE. We will organize a regional forum when everything is back on track with the COVID situation, and to actually share lessons learned from the pilot demonstrations with all the others to enable awareness raising, capacity building, and hopefully replication if this turns out to be a good solution. I would just make a summary. I would just say that the same properties that make plastic so versatile and valuable, like durability and resistance to degradation, also make these materials virtually impossible for nature to assimilate. So we are currently conducting an uncontrolled experiment on a global scale where billions of tons of plastic waste accumulates across all terrestrial and aquatic ecosystems on the planet, with unknown and possible dire ecological and economic consequences. We urgently need to identify some sustainable and cost-efficient treatment options for non-recyclable plastic waste, which can manage significant amounts in an environmentally sound manner. The involvement of energy-intensive industry like cement manufacturing can contribute, we have already seen that, to remove non-recyclable plastic waste and at the same time replace coal and reduce marine littering. So it's a triple win option, and which fits very well with our previous achievements. You know, in 2011, the Stockholm Convention, which is about persistent organic pollutants, they presented a book with success stories from the last 10 years of implementation. And we in SINTEF and co-processing had 2 chapters in this book. And one was about destruction of hazardous chemicals and POPs in cement kilns. And we have to remember that plastic might even contain, for example, persistent organic pollutants like flame retardants, which needs to be disposed of in a safe and sound manner. And last, I will just mention we had several presentations at this ongoing conference in Asia. It's called Semtech 2021, and it's about Asia's transition to a low carbon future. We had a presentation on Monday and a presentation yesterday, And I will just share with you the view of the organizer. They say, thank you for taking part in SEMTech today and for delivering. It has set the context perfectly for the rest of the conference, reminding participants why co-processing is so vital and the great potential for reducing pollution and CO2 simultaneously. I think this was very wise and I think fits very well as my last slide. So thank you for your attention.
Thank you, Kåre Helge. That was very both inspiring and nice to see all the pictures. It's kind of makes it easy to grasp the enormity of this challenge. So thank you. Next in line is one of the research partners in our project. He will give the first presentation on research conducted under the OPTOCE project. His name is Professor Vishu from the Asian Institute of Technology in Bangkok. And Professor Vishu is present here today to answer questions in the question and answer session. But he has made a recording of his presentations, which I will attempt to share now. I hope it works smoothly, but let me know if you cannot hear or see anything. Share.
Good afternoon, ladies and gentlemen. Let me take the next 20 minutes, make a short presentation and share our experience on this project on investigation of leachability and migration of plastic from the dump sites. My presentation outline is presented in the slides. Let me start with the AIT's contribution to OPTOCE and SINTEF projects, the dump site excavation and plastic brand auditing, microplastic analysis, and residual waste analysis. And also, I like to summarize at the end, what are the external impact or spin-off due to these projects and where we stand today. Let me start with AIT's contribution to the SINTEF OPTOCE project. And this work is done in collaboration with AIT's Environmental Engineering and Management Program with the collaboration of Geoinformatics Centers, which is located at AIT, which focus mainly on mapping and quantification of plastic and microplastic from the dump site to the nearby water body. We had two objectives. First one is classify and quantify the types of plastic amongst various solid waste fractions presented at two sampling locations in a dump site, doing a compositional analysis and aerial mapping technique. Second part, we also looked at it, quantifying the microplastic migration from the dump site to the nearby water body. This work is, as I said, conducted jointly with our geoinformatics centers. Especially, we want to spearhead this project using advanced technology. Here you can see one of the things is we could work our geoinformatics centers both 2D and 3D mapping techniques. Let me summarize the research status. We started the research in September 2020. It was the rainy season, and that is the time we looked at its sampling locations, okay, and also the initial drone flights, etc., had been conducted. And like in second part, in December 2020, we started looking at it, excavation and characterization of plastic from legacy waste at two different locations. And we also started looking at it, microplastic and residual analysis. Later, from January to February, we started working on it to a large extent, the location 3 and 4 of the categorization of the plastic waste. And you need to consider this is the time we were faced with the COVID-19 issues. So we had certain difficulty in terms of getting data. Later, last part from March to April, and we had this COVID-19 lockdown. In spite of the fact we were able to get more information and conducted. So in essence, we want to say that we have two difficult scenarios starting the research on a very wet rainy season. So we are difficult in getting samples. The later part, we could not have the access the way we wanted because of the COVID-19 and lockdown period. In spite of that, we were able to do a good work. And here you can see the research was conducted at Klong 3 or Klong Sam dump site, very close to AIT. It's located here. You can see an aerial view, a drone view of the dump site. This is the dump site, okay, which has approximately 16,000 square meter, okay, and the municipal solid waste is dumped here. It's not a landfill, dumped here from 2012, okay, and it is very close to. There's an irrigation canal which is eventually connected to one of the big rivers, which is called the Chauka River. And here you can see the dump site excavation. So here you can see the dump site has a total maximum depth of 3 meters, and most of the waste is put on the top. And it's also as important, we looked at it, it doesn't have sufficient coverage, and also the greenhouse gas emission was the thing. And if you look at it here, in terms of the dump site mining at Klong 3, we have the collection systems. The waste is brought into here, weighed, and it's dumped here within the dump site, and we have a trawl mill which separates a segment of the plastics, and the plastic separation is taking place, which later onwards shredded, and it is taken to produce refuse-derived fuel, RDF, okay, and taken to a cement plant. So we were able to take samples and analyze all this information also. And if you look at it in terms of sampling locations, so this is the dump site. These are the different locations. We collected the leachate so that we could look at the microplastics. And also we collected the samples on the canal, okay, which is just closer to the dump site. These are the sampling locations. And in terms of excavation, the plastic waste was excavated, okay? The way the plastic was, with the target of looking at plastics, how much is there in depth. Okay? So these are the locations, okay, excavated, okay, and the waste composition was looked into that. Essentially, paper, organic waste, paper, textile, wood, grass, and the plastic. As I said, our main focus was looking at it, the plastic on the different depths, etc. And here you can see the waste when it was excavated, and we need to do a sieve analysis. So we constructed ourselves a simple, practical, applicable sieve setup. Okay, and this is the sieve setup which could sieve the plastic between 200, 150, and 750, and then 50 and 25. Okay, so we could segregate the plastics on the thing. And here you can see when we took the sample, okay, we used the coning and quartering waste methods, and later onwards we did the sieve analysis. And it's also is very important, as we collected the samples, we were not able to do a sieve analysis. Very often it's a very wet, so we need to keep it dry for 2-3 days, only then we did the sampling. So let me sort of quickly give you some analysis in terms of municipal solid waste composition analysis. Okay. Here you can see very clearly in terms of from different depth, we were able to identify what is the year of dumping waste. So if you look at it here very clearly, originally the plastic in the waste was 17 to 18%. Okay, so if you look at it here in the dump site, this percentage is increases 34. You can see progressively the waste, the plastic waste components are increasing. That tells the organic biodegradable fraction is degraded, but degradation of wet organic, and which because of that there's an increase in plastic composition. Here then we also looked at it, the plastic classification based on the different polymer layers. Okay, and we also looked at it different types of plastics. Okay, starting polypropylene, PS, and PVC, etc. All the 7 categories. And we also looked at it, different plastic, try to identify which brand contributes the major plastic in the dump site. So it gives you some analysis of brand auditing also begins. So this sort of a slide summarizes the size of 25 millimeters was not observed between 2014 and 2015. So for other years, so you could see very clearly the amount of the plastic can be looked at it on different sizes. And it is very clear there is no significant change over the time, the plastic size across different years. That's very important. So the majority seems to have falling around 75 millimeter is the majority. And it's very important for you to understand. And we also looked at it in terms of moisture contents, okay, and etc., the calorific value. Okay. The key observation is with increase in the period of dumping, the volatile content of the plastic eventually decreases, which is quite normal because the organic fraction gets degraded, etc. So now we can look at it, the next part, plastic classification based on the resin code, okay, between the different years, okay, between 2012 and 2019. This is very interesting. The LDPE contributes to the largest fraction of the plastic. For example, PET and PP, it shows very clearly some of these things which have been very well recycled. So only these, the components which did not have any value, okay, were not removed. And one interesting thing in the recent years, if you look at it, multi-layer packaging seems to have increased. Okay, the new plastic products, something like this, have created a new problem. The issue of multi-layer packaging from dump site and their undesirability, because at the end of the day, we want to take this plastic for the refuse-derived fuel, considering the higher chlorine content originates from partially from the multi-layer plastic. I think that it is important that different multinational companies are responsible for producing this type of waste, which creates a new problem. And it also creates a new problem in terms of using them into an RDF. This is important. And here you can see that sort of a summary tells you for the different years, okay, and who are the major contributors, okay, in terms of plastic brand auditing and top producers. So for example, Tesco Lotus is a top polluting brand between 2012 to 2014. But if you look at it, 2019 and 2012, Palmyra is one of the biggest polluters. Okay, you can see what type of products. Okay, one of the another thing is Ajinomoto. It's very important. The multi-layer plastics comes in the small sachets, especially in Thailand. Many of these seasoning food comes in the multi-layer thing, and it's all come from essentially the food industries. It's very important, and there's a very little opportunity of recycling, but they contribute a large amount of plastics. Next, we looked at it micro analysis. We collected the leachate from the different places, okay, different locations, and we did the analysis, okay, micro analysis in terms of plastic. And this is quite interesting. And here you can see incoming waste takes you to the dump site. Then we have the ponds, okay, and from here some of the plastic which using the UV radiation and breaks down, some of these macroplastic become a microplastic, and eventually it starts moving along the line for the aquatic environment and eventually leads to the river. So we wanted to trace the plastic on different places. It's quite interesting if you look at the microplastic here in terms of size, and it is very interesting. The size ranges. Okay, if you look at it here, the size ranges from 0.13 to around 4 millimeters. It's quite important to understand that. And you can see the majority of the microplastic are in the order of 1 to 5 millimeters. Okay, this is very important. Okay, a size smaller than 1 micron seems to be very small in this case from the dump side. Okay? And it's also is very interesting. We also look at it, the major form, okay, and the different seasons in terms of fragments and the fibers, and we also form films and the forms are okay. And it's also important the forms which are available only on the wet season and it's varied in the dry seasons. Okay? So you can look at it very interestingly. We took samples on the wet season, and here we took the samples in the dry seasons. And it is very interesting. The fragments, let's say, for example, single-use plastics, it's with time disintegrates, the fragments becomes a thing. In terms of plastic, microplastic, polyethylene, polypropylene, and polystyrene are the most commonly used here in this case. Similar way, we looked at it in detail, different components. Okay, it's say the different sampling locations in the wet season and the dry seasons. You can see so it's very important. The predominant polymer seems to be in all cases polyethylene. Okay? Polyethylene and polysulfates are predominant polymer detected in the dry seasons. Okay, then followed by polypropylene. So it's very interesting observation. Now let's move to the last part, or the third part, where we use a single drum mill machinery was used here, where the plastic was segregated. Okay? So here you can see the drum mill and the size sieving, and we have collected the reject, and this is the refuse derived one, and what we do with the reject. And we looked at it very carefully. One of the interesting work we carried out here is how do you manage this reject? So in terms of the reject, it's very important. Dry reject fractions, which has a density around 570 kilograms per cubic meters, and which also consists of stones, plastic, garden waste, and etc. PET bottles. Now, one of the issues is what do you do with this? Okay, you need to look at it. So what we did is we did a composition analysis. We took the reject and we did again a sieve analysis using 3 different sieves from 17 millimeters, 12 millimeters, 9 and 7 millimeters, and looked at it whether this sieved one in terms of fertilizers, okay, whether moisture content, the gravels and etc. Different parameters we looked at it. We also looked at it heavy metals. Is there any primary nutrients available so that it could be used as a potentially as a compost. And the detailed analysis of this reveals, okay, where we took these samples and looked at it in terms of the compared with the Thailand's composting standard. It's quite interesting, the key observation, due to the high concentration of metal, heavy metal presence in the residue, and we can look at the other parameters, the utilization of this residue directly, it's not possible as a compost. So we need to look at it, some alternative, and that is one of the issue when we wanted to look at it, plastic recovery from the dump site and what you do. The third part of this work, we spent an extensive time using the modern technology, using a drone, a quantification, and also try to find out how much and what type of plastics were available. Okay, that is where we use this drone technology, and we were able to identify or quantify how much plastic is used above ground. Okay. It's quite interesting. We were trying to use this technology, and this drone technology need to be further developed, which will allow us to quantify any dump site, the amount of waste there, and also we will be able to estimate the potential of the plastic availability. I think we need to share this one. And one of the things we found out, the dump site was very difficult to work during the rainy seasons, okay, in our Klongsam dump sites. So it's one of the big problem because it's not a landfill, it's a dump site, it's relatively muddy and difficult to access, and it's also difficult to take samples. And also we had another problem in the COVID-19. Because of the COVID-19, most of the waste were dumped here, and it was a bit difficult and it's a bit not secure for us to enter the dump site. So we were a bit limited to get access to information. And it's also when you wanted to do in a sampling, and we need to do these heavy machineries, and that has a problem with us. And we like to thank NC EcoCycle, who are our partners. I think they helped us in the research work. And I also like to share with some of the spin-off because of this. I think they also, NC EcoCycle asked us to do some extra work, okay, in terms of analysis of chlorine content in the plastic products, which we recycle. And we also were able to get the data for them. I like to thank all my colleagues, the research partners of this research work. Now, please allow me to show you a small video.
Okay, I hope you all saw the video. Yes. Thank you so much, Professor Rishu.
Thank you very much. Thank you.
It was lovely, especially the video. It was very nice. I liked it. I'm sure your results will be of value both to the project, but also to industry and policymakers in the region, I would imagine. So thank you so much. And I know that a study from ISVA has shown that 38 of the 50 largest uncontrolled dump sites in the world are located near coastal areas. So it's obviously important what is in these dump sites and how much is leaking out. So I think this is a very relevant and good study. Okay, we are moving along in the program. Next up is another one of our dear research partners. It's Professor Sadan Ghosh at the Jadavpur University in Kolkata in India. Professor Ghosh is leading a OPTOCE-funded study at Jadavpur at the Center for Sustainable Development and Resource Efficiency Management. He is joined by his students today as well, I think, and I'm excited to learn more about your results so far. So please,
yes,
take the floor.
Yes. Thank you very much. Thank you, Visu, for your very nice presentation. And I want to share my screen. Share screen. Okay. And I hope this is visible now.
Yes, we can see it.
Anneli,
Yes.
can you see this? Yeah.
Yes.
So what I'll do is I have a presentation and then I'll show a very small video from here. So our research project is focused on mainly co-processing of non-recyclable waste in India. And what is the status of non-recyclable wastes, mainly plastics, in different dump sites throughout West Bengal, and we have taken some other state also, Bihar. So I have 3 researchers who are working in this particular project. And our main objective of this project is we have 3 areas. One is the survey of the people's participation on use of plastics, specifically non-recyclable plastic waste, and their use, reuse, and how this can be treated and disposed. This is one area with different stakeholders. The other area is how co-processing can be improved and how this non-recyclable plastic waste are utilized in co-processing in cement plants. These are the 2 main areas of concern which we have been working for a couple of months, and these are the areas of concern and the contents of the presentation. We have the researchers at the literature review, and they made a survey for understanding the people's perception through use of questionnaire, as well as they also visited different stakeholders like universities, hospitals, industries, municipalities. Then the second part of the study is identifying non-recyclable plastic waste in different landfill sites, and they identified those things in West Bengal and Bihar. Bihar and West Bengal are adjacent states. Then different analysis of the collected materials and the composition to see whether these are adequately can be used for co-processing in cement plants. And then the study of co-processing of waste, the status of co-processing of waste, and what is the procedure they are following, and how much quantity of non-recyclable waste can be used and are being used in the co-processing. So these are the things which are the part of our research. Of course, the publication is also. So our researchers made a literature review of in main 3 areas, around say 140 literature they have been working on, and with number of research questions, like you know that whenever we interacted with people, the first important thing is what is non-recyclable plastic waste. The definition of non-recyclable plastic waste is very much confusing. People don't know. So in that way, we have identified non-recyclable plastic waste as those which are not used by the people after the disposal, that we have identified as non-recyclable plastic waste. Of course, the multi-layered plastics are also some of the non-recyclable plastic waste that and then how it can be prevented from littering, how the marine littering can be prevented from this non-recyclable plastic waste. So all these things, then the questions are, what are the composition of this? How much is the non-recyclable plastic waste in landfill site? So all these things, and ultimately the how many plants in India are practicing co-processing, I mean the waste as AFR in co-processing, and what are the potential of increasing these in India. So they started the research in the month of November. However, one of my postgraduate student, he was doing research with me. So we started mainly from the month of August, September 2020, but formally the project started, work started in November 2020. The 3 researchers, we have first taken the survey in different stakeholders. Then we, January and December, you know, that we collected number of samples. You know that there was a lot of restrictions of visiting the landfill site by the people, because it was not allowed, because of the whole period of the project is under COVID situation. And even today in India, there are, I mean, in my city under lockdown up to 30th of this month. So it is really a very challenging to work under this, but however, we could manage to work to a greater extent. Then we had the first review, progress review meeting with Sintep. We requested them, and it had been there in December, possibly January, possibly. Then in the month of February, we went to different cement plants who were utilizing AFR, I mean waste in the co-processing, and we also visited some of the dumping site in Bihar. Then in March, the analysis of microplastic, though it is not onto our purview, but we tried so that we know what are the constituents and how the microplastics are affecting. But we collected the samples, but ultimately due to the problem in testing, we could not test it, but we have collected from the field. And then in April and May, we presented some paper in the conference. 2 papers was presented in the conference, and we also prepared some of the papers for publication. One publication is already done for a book chapter in CRC Press, and then in June, we have again started our work on some of the analysis, and we are also trying to visit at least 1 or 2 co-processing plant, and we have identified, they have allowed us to visit these plants in the month of August, early August. So this is more or less the status of our research. And as I was telling, that our work has been divided into different activities with a timeline. And these are the publications. These 2 publications, first 2 publications has been done in proceedings of 5th International Symposium in Hungary, Environmental and Quality Public Health. And the 3rd, legislative support to curb marine littering and co-processing in cement plants promoting circular economy, that will be published in a book, Effective Waste Management and Circular Economy, which will be legislative framework and strategies. That will be published and released in January 2022, but this is in the production process. So these are the papers which are under preparation by our researchers, 3 process. And now I'll request, I will involve my 3 researchers for the presentation, what they have done. So I'll request Shorjo to make a presentation on this quickly. Shorjo.
Thank you, sir. I will talk about our work on survey on the people perception of about their usage of non-recyclable plastic waste. So we did design a questionnaire and spread the questionnaire through Google Form on 270 individuals whose age were different. We chose individual on a random basis, and we asked many questions through our questionnaire. And we also did some survey on various school institutes and colleges, and we are still in progress. And we are also going to do some surveys on commercial and hospitals, but due to the COVID-19 pandemic, it has been very difficult to get access to those locations now. So about the results, let us come down to the results of a survey. We saw that in a household whose family member range from 3 to 4 in an average, the amount of solid waste generated was always less than 1 kg for the maximum of people, that is 67.2%. And onto those among those solid waste total, the amount of plastic was always less than 25 gram for 63.8 people of percentage of people, which is not actually a bad result. And from the survey, it was also concluded that people were more or less aware about the effects of the plastic pollution, and they were already started to using alternative products like biodegradable alternative products like jute bags and alternates. And people were also aware about the microplastics, that is the effect of the microplastics in our environment and marine life. But the deduction we made from the survey is that the general public has a leading role in order to reduce the usage of these pollution actually. And people has to be more aware to use more recycled products and recycle those plastic and segregate at source instead of dumping them. And with the right information and monitoring programs, this problem can be reduced significantly. Next slide, sir.
Yeah.
Now,
Go ahead.
now let us take a look at the sampling we have done on various dump sites in and around Kolkata and one dump site in Bihar. This is the map of West Bengal, in which the red cross shows the surrounding areas in which we have done some samplings of plastic waste from the landfill sites. We have visited 5 landfill sites, and we have generally applied the sampling procedure of coning and quartering in order to assess the amount of plastic waste in a fixed amount of solid waste, that is 64 kgs. This slide shows the dump yard in Pramod Nagar, in which we did some sampling. There is a daily accumulated waste of 315 tons per day in Pramod Nagar. Now shows the Boidabati dump yard. The Boidabati dump yard had a composting facility in which they were composting 15 tons per day, but the total accumulated waste was 55 to 60 tons per day there. Now let us come to the Boj. In these Boj, they had no composting or other processing, but the daily amount of solid waste was 30 to 35 tons per day. And this shows how we did the sampling. Now let us come to Dhapa, Rajpur Sonarpur. So in this dump yard, daily accumulated waste was 30 to 35 tons per day without any composting or other processing. So they gradually they were piling up without any processing facility. Now let us come to the biggest dump yard in Kolkata and its surrounding, that is the Dhapa dump yard. Here a total amount of huge amount of 5,000 tons per day has been accumulating every day, against which only a small amount of 400 tons per day has been gone to composting, and the rest is piling up there, building huge mountains of waste. And we also did some sampling of the plastic there. And after the collection of the data that we collected from the solid waste and the plastic, we collated the results, in which we found in a 64 kg of solid waste, there was 4.53 kg of plastic waste was found, which is generally 6 to 7%. That is not a very good result actually. So this slide shows the incoming waste in those dump site we have visited, and some of them were provided with composting, and some of them were not ready yet for composting. And moreover, we also went to Bihar in the state of Muzaffarpur, where we can see you can see some sort of photos of open dumping being practiced there. This generally represents that people are not aware of the plastic pollution that is, and there is also a composting facility, as you can see, provided with a trommel and and plastic waste was co-processing quite good, that is 15 to 14 tons in the March 2020. But this clearly sees that this shows that the sampling procedure, like the coning and quartering in Muzaffarpur we did. And let us come to the Boiddabadi municipality, where there was a composting plant where the composting waste were gradually stored for some months, like 4 to 4 months, then dried and converted into compostable, and they were sold at a ₹7 per kg, which is a good amount. And this business should be more more advised to do. Next slide. And this organic fertilizer belongs to the dhapa, in which I early mentioned. So they were selling their compostable products for 50 kg a bag at 350 rupees, which is not quite bad actually. It's very good for a business model actually. And now I would like to request my partner Abes Chatterjee to continue with the analysis of the plastic. Thank you.
Thank you, Shouro. Now we will discuss about the testing carried out of the waste plastic collected from the different dump sites. So we have tested plastic samples from different dump sites at 2 different testing laboratories. The compulsory testings for AFR taken to be the co-processing are our main focus of testing. That is moisture content, ash content, gross calorific value, sulfur, and chlorine content. These slides shows the report we have got from the first private testing lab. After getting the testing, we have testing result from the parameters. Firstly, they are matched with the CPCP guidelines. All of the parameters tested were follow the limits of the CPCP guideline. Although the GCV value is quite higher. Now these slides, the next slide shows the for the detailed testing of the plastic samples. We have sent to the plastic samples to the IISER laboratories. So this slide shows the analysis of the for analysis of the polymer content and identifying the types of plastic presents in the samples. We have done the FTR analysis. Their FTR graphs has been shown between the transmittance and the wavelength of the sample. So identifying the peaks of the samples molecular compositions, we have observed that the most predominant plastic types are the PET, HDP, polypropylene, PVC, etc. So the next slide. Next slide is this slide shows the moisture content which have been tested through international standard. The 5 different samples have been taken for testing with the weight of 5 grams each. So the mean value of the moisture content is for 8.48%, which is under the CPCP guideline limit, which is 20%. So that can be considered as a AFR for co-processing. So the next slide is ash content. Ash content is has been tested similar fashions, which is that is be observed there's a mean value of the ash content is 6.05%, which also falls under the guidelines of CPCB and can be considered as a AFR. So the next one is the for the sulfur content we have tested through the CHNS analyzer. So 5 different samples are approximate 1 milligram of weight have been tested through the analyzer. The sulfur contents for all samples have found 0 as the peak of sulfur have been found that there's no peak have been found. So that's also suggests that the sulfur can be the sample can be used as a AFR. Now the last part is the chlorine content. The chlorine content has been analyzed according to British standard. So 4 different samples have been taken for the sample with an approximate weight of 2 kg to 2 grams of sample. So the after analyzing this is found that the mean chlorine content of these samples are almost 3.62%. And also that is found that all of the samples have the various types of various content of chlorine due to the heterogeneous structure. So that can be recommended that we have to balance the PVC content, which is mostly due to the heavy amount of PVC content. We have to balance the PVC content, and that can be done through segregating the PVC. And after that, which can be used as a AFR for purposely. So now I would like to. This is the all of from my side, and now I like to hand it over to my fellow partner Piyush Chana for discuss the fair proceeding. Piyush.
Tejushi, do you have a problem? Arey, start it. Don't take time. Yeah, over to Tejushi.
Am I audible, sir?
Yeah.
Hello. Yeah.
Carry on.
So thank you, Avis. So I will now discuss about our study on co-processing of non-recyclable plastic in the 2 of the cement plant that we have visited in February month. So we have visited Dalmia and other UltraTech cement plant in the Ariyalur district of Tamil Nadu. So next, please. Next slide, please. So in this 2 particular cement plant, what we have seen that key, sir, please back. Previous one, sir. Sir, previous one, sir. No. The second slide, sir. Previous one.
Go
Yes,
ahead.
yes.
Go ahead.
Yes,
Please
yes.
go ahead.
So the size limitation for the acceptance of the waste was around 250 to 300 millimeter. It also varied as per the different cement plant, like UltraTech take around 400 millimeter. So after taking all the wastage from the municipality and the industries, they fit to their hopper in the alternative fuel and recovery plants. So there they have also a magnetic separator so that they can separate the ferric materials from the wastage. And both of the plant have their different procedure. Like in Dalmia, they have 2 shredder for the shredding, and in UltraTech they have the 3 shredders. So UltraTech having some fine material that is around 15 millimeter of size, while the Dalmia having a 75 millimeter of final product. And Dalmia having a capacity of 350 ton per day, but right now they are using around 30 to 40 ton per day. So as per that amount, they are using around 6%, but they have a capacity of 20%. In UltraTech, they are using 220 ton per day and having a TSR of 26%. The operating cost differs for both the plant due to their procedure. So for the Dalmia, it is 400 rupees, and for UltraTech, it is 600 rupees. And the capacity of cement production is 5,000 for Dalmia and the 3,850 for UltraTech cement plant. Next, sir. So this is the flow of the waste which they are taking from the companies like Jigma, New Age Environment Solution, DM Solution. So these companies basically extract the plastic pollution from the municipalities, and they are providing all these wastage to these cement plants. So the out of 220 ton per day, the Ultratech use 100 ton per day of the plastic waste. And out of this 100 ton, the 30 to 50 ton is for the plastic waste from municipality, and the left part is from the industries like food industry in the Pondicherry and the paper mills. And this as same, the Dalmia having a 350 ton per day, out of which they use this type of plastic waste from different municipality and the industry. And this is the type of the plastic they are using till now. And the below figures are what we have visited there for our study. Next, sir. And these are the approximate analysis of the different type of waste, like for RDF, the low moisture plastic having a more calorific value than the high moisture plastic waste, and the other waste are carbon black and resin waste. Next. And as same as the Dalmia, Ultratech cement are using lots of waste, and out of this, the plastic waste and RDF have this type of calorific value. Next one, please. And this is the parameters and the test methods they are using to test their samples. And the below figure is the figure of the lab of these plants. Next one. Yeah, and this is a graph from the Ultratech cement plant. So they have started in the 2014. So initially the actual consumption was less than the target, but we can see here that in 16 to 17 and until 19, they have crossed their target, but due to pandemic in 19 to 20, they have the target is not achieved right now. So that's all from my side. And now I would like to invite my investigator, Professor Sadhan Kumar Ghosh, to conclude the PPT.
Thank you, Tejasri.
Yes, sir.
So in that way, after this study, it has been revealed that awareness level in some of the cities which we have seen, and of course, if we extrapolate that is throughout India, the awareness level has been increased in last 5 to 6 years in the use, reuse, treatment, and disposal of plastic waste. But while plastic waste, the awareness is increased, but on the other hand, non-recyclable plastic waste, most of the people don't know what is non-recyclable plastic waste. So that is one area which has to be triggered much. There is a huge scope for the treatment of legacy waste. You know that many of the waste dumping yard and the landfill site which are existing in India and which has not been adequately used for further treatment. So in that way, we have the NGT, National Green Tribunal, who have pressurized the government as well as the municipality to go for the treatment of the legacy waste, that is the biomining and other things. So in that way, there are a lot of scopes for bringing different types of waste, specifically the non-recyclable plastic waste, which has a good calorific value for co-processing. And the third thing, India has taken a special drive by the government, cement plants, and related stakeholders to popularize co-processing of waste in cement plant, because it has been seen that the recovery of the waste in cement plant is maximum, nearly 100%. So in that way, this is one of the very important issue. And we are also, the government of India, also trying to popularize this among the cement plants and trying to make a business model so that it is acceptable to all the cement plants. And the fourth point, which we felt that research on co-processing needs to be strengthened. So with this, these are my researcher, Tejasri, Shorjo, and Abesh. I made them presented this PowerPoint so that they can also tell what they are doing and what are the problems they are facing, the challenges and other things. So with this, I like to thank the SINTEF for their support for this research. And of course, our research will have some other activities which will be carried out, maybe from, again, some practical field visit will be done from the month of August. So thank you very much. But after this, I'll show a video for 6 minutes. Mhm. Presentation. Is it visible?
You can see it, yes. Let's
Okay.
see if we can hear it.
All right. So hearing may not be possible. It will be in different language we put it, but okay. Some of the part is in English, so that can be seen here. Mm. Yeah.
में भी छांटने और चुनने का काम करने में
You know, this is the place which we call Dhapa, the biggest landfill site or the dumping site in Calcutta. And these are the plastics which are collected by different rack pickers, and this type of waste, the non-recyclable, recyclable plastic waste are taken for recycling, this type of plant, which are really polluting the environment as well as the health hazard of the people who are working in this place. So in that way, we devised improved technology. These are the processes which are happening in many of the parts of India, and of course in many other developing countries. So that is also one area of concern. So these people are doing all those things now.
Developed in this research project at our mechanical engineering department with the help of Central Pollution Control Board, New Delhi, and our Center for Quality Management was also associated in this research project. Now this machine gets its power from this power source. So this power source, it comes to the control panel, as well as it goes to the whole driving system. This one is the driving system. Now this control panel is having different thermostats which controls very minutely the temperature at each of the zones of this barrel. There are 4 zones in the barrel. Now, whenever the motor over here gets the power from this power source, through the pulley, the gearbox is driven, and from this gearbox, the screw inside the barrel is driven. So, in this barrel, the material is fed through this hopper. Now, this hopper gets the material, which are waste plastics, and we clean the material, sort the material, then we take the material from this hopper to the barrel itself. Now, you know that the first place where the charge is made is the barrel charging zone, where the temperature is around 100 to 150 degrees centigrade. I'll tell you the temperature of these different zones are depending on the material itself, whether you are using LDP, LLDP or PP. Now, from this charging zone, the material goes to the transition or compression zone. This is the point where the temperature varies from 150 to 175 degrees centigrade. And this material goes to the melting zone or metering zone. This is the transition part, that material goes to the liquid stage. Now, through this liquid stage, the temperature raises to 225 to 250 degrees centigrade in the dye zone. Now, this dye zone gets the material in melted condition, and through this breaker plate, it goes to the dye itself. Now, you can see that the whole dye, the dye divides the material flow into 8 circular cross section. It can vary, you can have it 6 or 10. Now this material through this cooling system goes to the cutting unit, where from we are getting the granules. Now let us come down to the pollution which are generated over here. Now this pollution to the atmosphere are really dangerous for the people, environment, and including the person who is working as an operator. Now we have taken the whole of the material through this duct to the system which we call our pollution control device. Now this pollution control device at its end is having a pollution treatment device. The uniqueness of this process is the whole of the pollutants treated in such a manner that we can make the byproducts out of these pollutants. So this process, whatever pollutants it is generating, this is the process. You can see the treatment zone, the zone where the pollutants are being treated, all the gases, and also the pollutants are converted into usable chemicals. Now, what we are releasing to the atmosphere through this is very much pure, and 95% of the pollutants generated in the process have been recovered and eliminated. So as a matter of fact, this process is very unique in nature, and this is the first in our country, the process which can be adopted by the recyclers of our country. You know that this is one of the most unstructured business area, which involves a lot of products. These products are having very good market in our country and abroad also.
So this is the one plastic recycling process which I developed, and I got a patent also for this. But of course, it is not a part of the project, but I thought that this will be helpful for the people who are here for general awareness. And if this type of process is also adopted in the country, apart from the non-recyclable plastic waste, these are all applicable for the plastic waste. So with this, I thank all of you for your patient hearing. Thank you very much. Over to Anneli.
Thank you so much, Professor Salam. That was very, very interesting presentation. And I'm, as with the Dr. Vishu's presentation, I'm very impressed by how much you have gotten done despite COVID restrictions and everything. You have so many results already. So
thank you. Thank you.
Very interesting. And your students and researchers seem very enthusiastic and clever. So I'm sure the final results will be great as well.
Yeah, that's why I made them to make a presentation here so that they are encouraged. No?
Yeah.
Thank you.
Lovely. Okay, we're a little behind the schedule, but that's fine. We'll just cut down on the Q&A session. We have some time there. Next up is Professor Yan Dahai from the Chinese Research Academy of Environmental Sciences, called CRAES, located in Beijing in China. They are a research institute under the Ministry of Ecology and Environment in China, and they are our research partner there. And as Kåre Helge mentioned, in China, we have conducted one pilot demonstration, and we've done the research study together with this pilot demonstration in a very scenic and beautiful village called Zigui along the Yangtze River. But I will let you, Dr. Yan, explain the details in this. So please.
Okay. Good afternoon, everyone. Now it's 4 o'clock in China, so it's a good afternoon, everyone. Let's share my screen. Which one? Sorry, I should find them. Okay, find them. Okay, can you see them?
Yes, perfect.
Okay, but it's too. My presentation title is co-processing of non-recyclable plastic waste in China. I will introduce two pilot co-processing tests on non-recyclable plastic waste, actually it contained 4 kinds of non-recyclable plastics in two cement plants. Until now, we have finished 1 test, and the next is ongoing. Sorry. My presentation include 3 parts. First, I will introduce the first test, co-processing test of floating material from Yangtze River and RDF. And second, we will introduce the co-processing test on non-recyclable plastic waste in Jilin. This is another plant in China. And the third, we will introduce the next work plan of our project in China. Too quick. The first part, we conduct the test in a cement plant nearby the Yangtze River. That's include 2 kinds of non-recyclable plastic waste. First is floating material. The second is RDF. What's the floating material? Is come from 2 sources. One source is come from the solid waste along the Yangtze River. When there is a rain season, this solid waste will be washed into the river, into the Yangtze River. And the second source is human throwing. People like fishermen and tourists also throw the waste into the river. These 2 kinds of the waste has been called floating material in China. You know, there is in Yangtze River, there is the biggest biggest dam in the world called Three Gorges Dam in Yangtze River. During the flood season and the importance of the Three Gorges Dam, a large amount of floating material from the upper Yangtze River was carried down by the flood and gathered in the waters near the upper stream of the Three Gorges Dam. This is called the floating material. This floating material make the dam very dangerous if we do nothing about them. Also, when the ship go across the dam, this floating material also will go to the ocean alongside the ship. Yeah, sorry. The amount, how much every year generated of this floating material, it's about 80,000 to 1 million tons every year generated for this floating material. This picture shows the floating material, and the first, the upper left, shows the material just alongside the dam, and the second picture shows how we collect it. The comparison of the non-recyclable plastic mainly contains plastic bags, plastic bottles, and shoes, etc. Also include crop straws and branches, and also other floating materials such as animal bodies, navigation marks. But most of them are plastic bags and plastic bottles and shoes. This is the comparison. How we collect it in China? This floating material are collected by floating garbage ship by a ship, and collected manually just with hand, and collected onto the ship and transported to the dock. Yes, I can. After collecting this floating material, how to treat it and how to dispose of it. In China, all the floating material was co-processed in a cement plant. This cement plant is called Huaxin Zigui. This plant belongs Lafarge Holcim Group, the biggest stockholder is Lafarge Holcim. So this work was done since 2010, and all the pollutant material upstream of the Three Gorges Dam were co-processing in this plant. And what's the process? First, the polluting material are transported to the drying workshop of Huaxin Zigui cement plant from the dock and dried by the waste heat of the cement kiln. This waste heat from the grid cooler. This waste heat from the grid cooler of the cement kiln. And when the pollutant material is not too much, this pollutant material also was piled under the sun and was dried in the air. When the pollutant material is too much, they were dried by the wasting heat. Then, after drying, they were shredded by a shredder and fed into the cement kiln by a belt conveyor. This picture shows the machine, shows the process. The first is the shredder for the pollutant material. The second is the pollutant material after shredding. It's about 50 millimeter, and the smallest is about 20 millimeter. And then it was weighed by a belt weight meter and transport by a belt and feed into a receiver hopper. Then they goes through an airtight door and feed into the precursor of the cement kiln by a feeding duct. This is the device. This is the facility and device for feeding of the Yangtze material from Yangtze River. And the second non-recyclable plastic we feed is about RDF, and the RDF is produced from municipal solid waste pre-treatment plant in Zigui, and this municipal solid waste was generated by the villages alongside the Yangtze River. That means if we did not treat the municipal solid waste, this solid waste will flooded to the Yangtze River and finally go to the ocean. So we must collect it and treat this RDF. And the RDF production amount is about 12,000 tons every year. And the composition, most part of it are non-recyclable plastic waste. Most are plastic bags. The right picture shows the image of the RDF. Most plastic bags. And this picture shows the RDF making process. We call it bio-dried process. First, the raw municipal solid waste was shredded. After shredding, this municipal solid waste go to the bio-drying process. Bio-drying process also be called fermentating. The air was blowing into the bio-drying plant machine. After the bio-drying, the municipal solid waste become very dry. And during the bio-drying process, some liquid was producing, and this liquid was collected and feed into the kiln. And the odor also generated during the bio-drying process, and this odor also be treated by bio-treat method. And for the drying municipal solid waste, it was shred and sieved and sorting. It was be divided to 3 parts. The first part is a combustible part. We call it RDF. This was fed into the precursor of the cement kiln, and the inert part, which was fed into the raw material, raw meal into the cement kiln, and the metal was recovered. For this test, for this demonstration test in our project, we just feed the combustible, also called RDF, in the cement kiln. This picture shows the process of the bio-drying process. The first picture is the bio-drying site, and the second picture shows the shred and the sieving machines. And the third is the older bio-treat facilities. The last picture shows the RDF, the final product RDF. The particle size also from 20 to 50 millimeter. Next, we use these two kinds of non-recyclable plastic waste. One is the floating material, and the other is RDF to conduct the test, demonstration test. The cement plant, the cement kiln we use is about 4,000 tons per day cement production capacity, and the feeding for RDF is 240 tons per day, and the floating material is about 200 tons per day for the feeding rate. Why we conduct this demonstration test? We have two objectives. The first, we want to compare the overall performance, such as the process parameters, emissions, and the product qualities under baseline condition with co-processing condition. What is the baseline condition? Baseline condition means feeding only coal as the fuel. And what is the co-processing condition? That means feeding floating material or RDF as a fuel. The second objective is to make an estimate of the cost efficiency of using floating material and RDF compared with oil only, and estimate how much coal is saved. In other words, we want to know the TSR. This is a test plan, procedure. We conduct this test in 3 days. Every day have one condition. First day is called baseline condition. We only we only feed raw material. We only feed fuel and raw material. We stop feeding RDF and floating material at 0 o'clock. And in the morning, about 10 p.m., 10 to 18 o'clock, we take the sample. The sample includes the flue gas, coal, raw material, clinker, kiln dust, and we also record the related data. And the second condition we conduct in the third day. In the second day, we stop feeding the fuel. No, sorry, so not stop feeding the fuel. We just feeding the floating material and the raw fuel, raw coal together at 8 o'clock, and after stabilization the kiln for 2 hours, we sample the same atoms, for example, flue gas, coal, raw material, and record the related data. And during feeding the RDF floating material, the cement kiln opened the bypass system. So we also sample the bypass dust during the second co-processing condition. The third condition is co-processing RDF only. We stop co-processing floating material. we just feeding RDF and natural fuel. The time is the same as the last day. We sampled the atoms, all kinds of samples during 10 to 18. This is a test plan. And this chart shows the atoms we analysis. First, we analysis the waste and the coal. The atoms include sulfur and heavy metals. That heavy metals include 16 heavy metals. And we also analysis the chlorine, heat value, fluorine, water, and ash. And also we analysis the plastic content in the pollutant material and RDF. This is for waste and coal. In the same time, we analysis the polluting volume, oxygen, water, dust, sulfur, oxygen, carbon dioxide, and hydrogen, fluorine, dioxin, heavy metal, such as this in the chart in the flue gas. We want to know feeding RDF or feeding pollutant material, the impact on the flue gas for feeding when feeding this material, when feeding RDF and the pollutant material. We want to know this, so we sample the atoms in the flue gas. Also, we sample and analysis the clinker quality, heavy metal leaching, and heavy metal concentration in the clinker, and chlorine concentration in the clinker. And we also analysis the dioxin concentration, chlorine concentration, and heavy metal in the killing dust, and the dioxin concentration, heavy metal, and chlorine in the bypass dust and in the raw material. So after we analysis this, we want to know the chlorine route in the cement killing, and the dioxin generation, dioxin generation in the cement killing. We want to know this, and also we want to know the heavy metal route in the cement killing. So we analysis such kinds of the atoms. Also, we record the production data, such as the co-feeding rate. This includes the killing head and the killing inlet feeding rate, and the raw material feeding rate, and the clinker production rate, pollutant material feeding rate, RDF feeding rate, and the bypass dust generation rate. All kinds of the material flow rate we will record. This picture shows the test progress. The left is the pollutant material in our sampling place, and the second picture shows the RDF storing place when we sampling. The left picture shows the feeding point of the plastics, which includes the RDF and the pollutant material. That's the feeding into the silo, and then it was being transported by the belt and go to the pre-chem center. The right is the belt. This picture shows the material, floating material sampling. We collected and divided into two parts, and selected the plastic content and weight it. After weighted, and we crush it into powder for analysis. This is the RDF sampling. We also collected and divided into four parts, and selected the plastic part and weight and thread, and make it into powder. This is a sampling of solid samples, include the bypass dust, coal, and killing feed. Killing feed also is called the raw material into the killing. We sampling all kinds of the sample, solid sample. This shows the flue gas sampling. There's a lot of devices to sample. The test I just introduced, we have finished. This test, then I will introduce the second test. This test have not been conducted, so it's just a plan. It's just a plan. We conduct the test in another cement plant located in Jilin. This plant name is BBMG. This cement plant is nearby the Songhua River. It's a very large river in China. I think it's the fourth or fifth largest river in China. And the cement production is about 5,000 tons per day. And we co-processing two kinds of waste, plastic waste. The first plastic waste from the paper recycling plant. The waste packing. This paper recycling plant collect the waste packing. The waste packing alongside the Songhua River is collected and transported to the waste paper recycling plant. In this plant, the waste packing is soaked in water. Then the plastic was separated from the paper. The paper was recycled to produce new paper, and the plastic we call the non-recyclable plastic was collected and co-processed in a cement plant. The second kind of plastic comes from the landfill site. This landfill site is a very old landfill site and was closed. So this plastic waste was sorted from this old and decayed municipal solid waste. The amount of this decayed MSW is about 1,500,000 cubic meters. It's very huge. It's very huge, and the composition of this this material is most of the are non-recyclable plastic waste. Most are plastic bags. Where we choose this plant conduct this test because this plant located nearby the Songhua River. If we do not collect this material, plastic material, this material will maybe go to the Songhua River and go to the ocean. So we must collect it and find a suitable way to treat it. This picture, the upper line, the upper two pictures shows the plastic waste from paper recycling plant. Most of the content are plastic. And the second, the lower three picture shows the plastic waste from the landfill mining. This just was sorted from the old and decayed MIW. Most are plastic waste. Until now, we have not conducted this test. The main reason because the machine in the cement plant is not okay. It's not good as we thought. The first picture shows the feeding machine of the RDF, not RDF, feeding machine of the plastic waste, and the left picture shows the visiting and the meeting when we conduct this project. Also, we designed this test for three conditions. The first condition is the baseline condition. We just feed the coal, and the second condition is co-processing landfill mining. From the plastic waste from landfill siting, we only feed coal and the plastic waste from landfill mining. And the third condition is co-processing plastic waste from paper recycling condition. We only feed coal and paper plastic waste from the paper recycling plant, not feeding the plastic waste from landfill mining. We designed the 3 condition. The analysis items and sampling frequency is the same as the last condition, last test. We will not repeat it. Finally, we want to introduce the next plan of our project. First, we will finish the report of the Huaxin Zigui cement plant in this month. Until actually now we have finished all the report, but this figure, this data, we have not reported to the same time. So in this meeting, we will not introduce to you. I think in the next meeting, I think we can introduce this data to everyone. Then we will conduct the second pilot demonstration in BBMG cement plant. But from the recently information, this cement plant, the feeding machine of this cement plant is not as good as we thought. The feeding rate is too low. So I'm considering to change another cement plant to conduct the second plant. We also use the plastic from the old closed landfill site. In China, there's a lot of old and closed landfill site. I think we will sort out the plastic waste from this landfill site and conduct the test. Finally, we will complete the project. This is our plan for this project. Thank you for your listening. I'm finished. That's all.
Thank you so much, Dr. Yan. That was very interesting. And I think this study in China, it really shows like the potential of co-processing in reducing these enormous volumes of plastic that's flowing from rivers to the ocean. So I think this is a very, very good and relevant study. So thank you so much. Next up is the last research partner before our questions and answer session. And that is Dr. Trinh from Vietnam National University in Hanoi. And he is leading 2 studies that is funded under the OPTOCE project. If you are ready, Dr. Trinh, I think you can just begin.
Yes, yeah. Thank you, Elali. Can you hear me?
Yes, we hear you very well.
Okay, so yeah, please a moment, I will share my presentation. Yes. Right. Can you see?
Yes, we see it.
Okay. Ladies and gentlemen, dear professor, colleagues, my name is Trinh Deputy Director of the VNU Key Laboratory of Advanced Materials for Green Growth at Vietnam National University in Hanoi. So today, on behalf of the research group, I will present the summarize of the obtained result that we conducted within our research group as part of OPTOCE project. So we are working with the 2 titles, with 2 master students, and the objective is to identify and quantify the non-recyclable plastic waste generated from different sectors and their behavior in the dump site after the ending up in the dump site and landfills in the north of Vietnam. So my presentation includes the context of plastic waste in Vietnam, and then I will present the plastic waste sampling, of course, survey at different sectors also, and then to the physical chemical calculation of plastic waste to figure out the composition, the type of plastic waste, then non-recyclable and recyclable plastic waste from different sources and dump sites and landfills. And then we present the analysis of the different pollutants in the niche samples in the dump sites and landfills. Then this results in discussion, and then finally I will have some conclusion and ongoing research activity. Yes, so before presenting the results, so I would like to inform you that our research activity conducted in Vietnam National University, we almost finalized all the activities, and of course, because of the COVID-19 pandemic and new outbreaks in the north of Vietnam, there are some analysis, but only in the laboratory, have not yet conducted, and some have not yet ended finalized. So we need maybe 1 month more to finalize every analysis to have the final report. So yes, as you know, in Vietnam we are in very fast urbanization and the industrialization, with a lot of challenges also, including the solid waste and plastic waste, which are about 100 million people. You can imagine a lot of waste and plastic waste generated each year. So in Vietnam, we have a figure of around 2.5 million tons plastic waste disposed each year, and the about 0.7 million tons of plastic waste end up into the ocean. And on average, each household generate about 1 kg of plastic bags per month, and mostly the two biggest cities, Hanoi and Ho Chi Minh, discharge about 80 tons of plastic waste and plastic waste to the environment each day. And Vietnam, as you know, we are in the top 10 largest generator of plastic waste and plastic waste to the ocean. As you can see here, Vietnam, we generate about 0.7 million ton of plastic waste to the ocean. And in terms of the disposal, so the sorting, recycling, and disposal in Vietnam is still very limited. There are about 10% of the plastic containing in domestic solid waste, and the recycling is very low rate, and mostly buried or burnt in open air or in the dump site and landfills. Here you can see some pictures illustrating the plastic waste in different coastal area in Vietnam, and a lot of information are already published in different areas. So as part of the our research project, we would like to identify and quantify the non-recyclable plastic waste from the generation sources, and then their property, behavior, and the dump site and landfill. So at the first approach, we study the generation of plastic waste from different sectors like household, household businesses and school, university, and supermarket, and finally public parks in the central district in Hanoi City. So you can see different figures for different sectors that we conducted survey. We interview the people and then collect the sample and stores the sample in the laboratories and analyze later on. And then to know their behavior in the dump site and landfill, we conducted our research at 4 dump sites and landfill in 3 provinces and cities along the Red River, the longest one in the north of Vietnam. So including Hanoi, Bắc Giang province and Nam Dinh province. Nam Dinh province is Kota province in the north of Vietnam. Here you can see some picture on the dump site in Nam Dinh province that we conducted the survey and sample collection. Here is a second dump site in the Nam Dinh province, but another district. That we conducted the sampling and survey. Here's another some pictures in Bắc Giang province that also we conducted our study. Now here's this one is the some pictures that we took in the Nam Sơn landfill, the largest one in the north of Vietnam, with about 160 hectares, and each day it receives about 8 million cubic meter of municipal solid waste. And this one is very is strictly to the people outside the landfill that can enter to this to the site. So we need to have a permission to work in, and also we are limited to take the picture, so we have only some. Here these are some plastic samples that we collected from household, school, market. We collected a lot, but here's only some picture. We could not collect all the sample at one time, but we divided in different times so that we can prepare the sample for analysis one by one. Otherwise, it's too many sites, so it's too difficult to prepare and analyze in our laboratories. Here are some pictures about the wastewater that we took from different dump sites and landfill in 4 sites. Yes, so now I would like to move to the categorization of plastic waste. Yes, this one, these pictures illustrates the sample preparation. So we collect the sample and then we watched this, and now we firstly we separate different types of waste like glass, plastic, cotton, textile, etc. And then we figure out and calculate their proportion, and then we select only the plastics waste to wash them and dries naturally and later on for the further analysis. Here you can see some pictures about the washed plastic. Yes, and we dry in dry them before other further analysis, like yes, and here is a procedure for identify the type of plastic that you can see firstly, first step, we use a limonene to figure out the PS and non-PS plastic waste, and then other break test and acetone for separation of PC and other PVC, PE, and PP plastic test. Of course, we use also the density of the different plastic waste to separate them. That is a approach we use. We use another simple approach to see that that sample is the thermoplastic or thermoset. So we heat a stirring rod and then press it against the sample, a plastic sample, and then we can see if it softens, and then we can roughly say that it's the thermoplastic. And then if there is no reactions, and then we can say that, conclude that it's a thermoset. And then we hold the sample to the flame to observe the burns of sample, etc., to see the smoke and write the information that we observed. The two approaches allow us to know the type of plastic, thermoset and thermoplastic, and some other information on type of plastic, and then we need to confirm if they are exactly the plastic that we analyzed before. We need other further instrumentation or analysis in the laboratory. So here we use the premises and instruments in our key laboratory, including the SCM EDH to analyze the surface morphology of the plastic waste and elemental composition, and then the FTIR for the functional group to confirm that is the plastic that we found or not. And then the XRF to analyze other heavy metal that contain and other elements that are contained in our plastic samples. Yes, and other also here's other equipment that we deployed to quantify and analyze the plastic sample. And now I move to the results in discussion. Regarding the FTIR analysis, here's two examples that we found the different functional group of the CH scattering vibration and CS bending vibration. And then we, of course, we need a library to see the information and the different brick for pure plastic or commercial plastic. Yeah, but we have not yet put it here, but we can conclude in the left-hand side that that's linked to a polypropylene, the PE, and to the right-hand side, that is a PP. And of course, this information with the results that we obtained previously allow us to conclude the type and the name of commercial plastic in our plastic waste. And also this one is a PS. Then we look at the morphology and elemental analysis, and we can see that in most plastic waste are very smooth, and the we have only there are many containing only the carbon and hydrogen, and then you can see their proportion of carbon is 100% because the hydrogen is could not detected by this method. But you can see other, for instance, this one, you can see the carbon and oxygen contained in our plastic waste. It means that that is not the PP or PS or PET, but maybe the carbonate plastic waste. So we need to work more on this one to figure out the name of the plastic waste. So all of them are confirmed by also the XRF analysis to analyze the heavy metal or different element on this on our plastic waste. Yes, I don't present all other information regarding the proportion of other waste in in the waste we collected, but I only present the plastic waste in the waste we collected from different sectors, generation sources such as household, school, supermarket, and dump site, etc. So we can see here almost all the generation source present the PP, PETs, and PE. So almost all of sector generate the have the presence of PE, PP, and PETs. For the dump site and landfill, you can see their proportion even increased a lot with, for instance, PE and BP with 55% in the dump site and landfill. But we can see also the PET. We didn't observe the presence of PET in the dump site and landfill. Only very small proportion in a dump site in Nam Định province. So that means that maybe the a large proportion of the PET are already collected and separated to recycle before ending up in the dump site and landfill. And here there are some results and information about the pH, turbidity, the COD and DO in different dump site and landfill. So we collect the wastewater, and then we see the pH around 8. The COD almost higher than the limit, and mostly the DO, the oxygen demand is very low. Yeah, we analyzed also the heavy metal. So as you can see in the table, that the concentration of heavy metal are very low. So almost no concern about the heavy metal in the dump site and landfill that we study. There are, of course, some, but linked to the manganese, that is not really high, also not very high, even that is higher than the limit, the detection limit, and not they are not close to zero, but concentration are not that much. So we have to conclude, the combination of conventional physical chemical methods and instruments to measurement by FGIR, SCM, EDI, so with the XRF, allow us to identify and the presence and quantify the proportion of different types of plastic waste generated from different sectors, and the plastic waste collected from dump sites and landfills. All the plastic waste generation sources contain the PP, PE, and PETs, and some PVC. Dump sites and landfills contain more various types of plastics compared to generation source, and most of dump sites and landfill contain the PP and PE. However, the PET is rarely found in dampsite and landfills. Of course, turbidity, COD, and DO are very high concentration in the dampsite and landfill. So for further research, we need to finalize the analysis in terms of energy. Calorific power analysis. And then once we have information about that, we can conduct the mass flow analysis based on recyclable and non-recyclable plastic waste. And then we will have a report writing and a master thesis defense by December this year if the COVID-19 situation is controlled. As you know, we have the COVID-19 outbreak in the North Vietnam around 2 months ago. Yeah, and now the situation in Hanoi is getting better. So we hope that our students can come to university to work, but since almost 2 months, they could not work in the university. So in terms of research in the dump sites and landfill, so we are working on microplastic analysis. We have our instrument, but the procedure we have also, but it's a little bit difficult. It's a time consuming method that we need much more effort to analyze correctly the sample. So that is why I would like to discuss with our other colleagues on this issue because that is really challenging. And we will analyze also some other organic pollutants as the POP, organic persistent compounds, and we will go to the final data treatment and for the report writing, and also another master thesis defense by December of this year. So for the second one, maybe the second one can defense in this October, because the results is almost finalized, but we hope the situation is better and they can come to school for the defense. And we managed to submit at least one article in the ISI and Scopus journals by December of this year. That depends on situation, but at least one by the end of this year. That it may be in this September or this October, but at least in December. Here is our research team. There are Tom, a master candidate, and Mrs. Quỳnh Anh is a master's candidate. So they are both involved in the two topics that we are conducting within our pre-laboratory. With other research, they support and work in collaboration with the two master students. So I would like to express our thanks and gratitude to Cinti to support our research as part of the OPTOCE project, and thank Dr. Kea Kassensen, who worked closely with us since last year, September, October, and we hope that we will have a fruitful results and outcomes soon. Thank you.
Thank you so much, Dr. Trinh. That was really, really interesting to see everything that you've done. And yeah, I can't wait to see the final results as well. And I think I'm speaking for both Corel and myself when I say that we're very excited about coming back to Vietnam and actually meeting you in person at some point. Okay, now we have a very short time for, let's see, a very short time for some questions and answers. For this session, I would like all the speakers to turn on their camera so that everyone can see them. And we got some questions in the chat. I think I will prioritize to ask some of those questions. And then, as I also wrote in the chat, the questions that are not answered will be sent to the speakers by email so that we can comment on them in writing and circulate to the audience. So it's still possible to ask questions, of course, that will probably be circulated by writing. But I think I will start with the first question to Kåre Helge. And that's coming from Bruno in EcoCycle Vietnam. He was asking while you were presenting, is there any estimation of CO2 emissions reductions overall if we replace fossil fuels, such as coal, with non-recyclable plastics?
Not that I am aware of. We have some estimates, internally, but we don't have any official figures. And of course, you have to, in a way, be aware that, of course, plastic as such is fossil fuel based, so it will not immediately reduce the CO2 emissions. But if it's part of, for example, refused derived fuel, it might be reduced up to 25% according to the IPCC guideline, etc., etc. So when we are talking about CO2 reduction by using non-recyclable plastic waste, we are basically talking about, what should I say, intermediate or other forms of reduction by avoiding, for example, building new incinerators or building new landfills or letting organic waste degrade in landfills and create methane, etc. So it's a kind of indirect emission reduction, basically. But this is due to the scheme developed by the IPCC, which is not directly, acknowledging that, for example, if you reduce coal by waste, like non-recyclable plastic, you don't get really the CO2 emission reduction benefits. So it's a little bit complicated. So I would say, as of now, and this is something we will work further on with, but as of now, it's a kind of indirect reduction, but it will be substantial, I am pretty sure.
Great, thank you. I'm going for the next question. That's from Simon at AIT. I think this was probably going to Professor Vishu or maybe Kåre Helge, we'll see. When talking about plastic mining at dump sites and landfills, is the concern of methane emissions considered when disturbing high organic carbon loaded sites?
Yeah, maybe I try to answer that. Yes. Yes. If you look at any dump site, if you don't mine it, what you release is a continuous release of progressively a methane. So it will take a longer time, but you will continuously emit methane. But because of the mining activity, to a large extent, we make this dump site to a more of an aerobic condition. So the emissions are CO2. So the issue is whether rapid emission of CO2 or slow continuous emission of methane. We need to calculate this. We have not done it. So I think this is what happens. So in fact, if you ask me, a landfill mining and taking plastic out essentially reduce the greenhouse gas emission in any dump site. But we have not measured or we are not quantified, but we are working on this, how to quantify this information. Is that okay? Any additional information?
No, I would agree with you, Professor Vishu. I think overall this is beneficial, not only for emissions or greenhouse gases, but also for groundwater pollution, release of microplastic, etc., etc. So I think this is beneficial. But I think, this probably deserves a little bit further in-depth calculation. And maybe this is something we can look into the next year.
In fact, currently we are working with INSEE, eco cycle to how to quantify these GHG emissions. So we have created a sort of a template, and we will not be able to share it because it is part of the company's property. So, but if anybody is interested, we'll be happy to share the process.
Wonderful. I think I'll take the time for one more question for Professor Trin. Surya has asked you, I'll first commented excellent research and then wondered what procedure was followed while collecting the samples.
Yes. Thank you. For selecting the samples, we have two types of samples. That is from the generation sources, household, school, supermarket, and public parks and dump sites. Okay, so two dump sites and other 5 sectors. So for the household, school, and the supermarket, so we conducted the survey, so we came directly to the household, etc., ask a question to have all the information about the generation of plastic waste, and then we gave them a plastic bag, very last one, and then we gave them the evening of the in the evening, and then the next day in the evening, no, not evening, but 5-6 o'clock in the PM, we came there, and then we collect our site. So to assure that we will have the 24 hours collection of their waste. So for instance, today I come to the house around 6-7 because around 6-7 all the people will go back from their office and their work. And then in the evening they will cook at home. And then they will generate the waste, including plastic waste. So all of the waste we put in one sack. Okay, and then the next day at 6 o'clock or around 6-7, we came to their house or school, the same, and then we collect the sack. So we collect the sack to our laboratories, and then we separate all the types of, we sort all the types of waste. So plastic, glass, textile, paper, etc. And then we to figure out the proportion of each type of waste. That is first information. And second one, we will collect only the plastic waste. And then we wash plastic waste, and then we separate and we dry the plastic waste, and then we store the plastic waste for further analysis. So a type of plastic waste, and finally the name of plastic waste. So finally we will have a non-recyclable, not only non-recyclable and recyclable plastic waste, but also the name directly, the name of plastic waste. That is for the generation sources. And for the dump site, we conducted so for each dump site, we collected wastewater and waste in general at three level at a dump site. For each dump site or landfill, we collect at 3 level. So from the surface, no, from the around 50 centimeters from the surface, okay, to down to 50 centimeter to 1 meter, we will collect a sample. And around 1 meter depth, we collect another sample. That is 2 meters from the surface, 2 meters. And then 3 meters, we collected another sample. Okay, so at 3 level, around 1 meter, 2 meter, and 3 meter. And then we collected both solid waste and wastewater. So for the solid waste, we sort also, we separate at that. We collect all of them in a sack, and then we separate again to sort the plastic waste, proportion of plastic waste, because that is not only plastic waste, but that contains other brick, glass, I don't know, textile, etc. So we need to separate all of them and then to weight to see how much proportion of each type of waste, and then we work only for the plastic waste for further analysis. That is for plastic waste. For the wastewater, so at 3 level, 1 meter, 2 meter, and 3 meters, we analyze heavy metal and many other factors that you already see, and we also collected the water around the dump site to see if there are any pollution that leads to the river or other other areas around the dump site and landfills. That is why that is how we connect the waste.
Perfect. Thank you. Thank you. Okay, I think we don't have time for more questions, unfortunately. I think we could probably keep going for several hours with questions. There are still a lot of them in the chat, and I have several about the way forward and synergies that we see. So I think we need to set up another meeting with especially with the partners in the academic collaboration. But now we are moving on, and as I said, the questions will be circulated by email, so you can expect some answers in writing after the webinar. But now we will move on to our final contributor who has joined us. That is Professor Tamarat Kutatep from the Asian Institute of Technology in Bangkok. And Professor Tamarat, he is heading the newly established graduate program on marine plastic litter in Asia. That's called the Marine Plastic Abatement at AIT. And the OPTOCE project is part of the steering committee of this program, which we're very proud of. And he will share some of their results and experiences from the first year. So welcome, Tamarat.
Okay, thank you. Thank you very much, Anneli, Kale, and the others that joining this session. That would be really interesting. I could not join in the early stage because I have occupied with the other webinar. So I think Professor Vishu has been introducing to you about that, the research part. But I'd like to introduce to you the academic parts that we have done through the one-year master program in the marine plastic abatement. So I will brief you a bit to the background and also the activities we have done so far within a year time. Okay, can you see my slide?
Yes, we see it.
Okay, thank you. So actually, this is the projects that we got the support from the Japanese government, that we try to empower the new generation readers that very much focus on the marine plastics abatement. Certainly, Dr. Kale is one of that our board, so-called advisory board, that helped shaping up the program, and then we like to launch this in a way that we can address several issues apart from the expertise from the AIT. So this program, we have the support from the Japan for sure, but we have to follow the kind of the initiative, so-called the Marine Initiative. They call it Osaka Blue Ocean Visions, that announced in the G Summit 20, that G20 Summit that in Osaka. So they addressed that the vision aiming on the management of the waste, recovery of the marine litters, innovation, and the last one is empowerment. So I think you may have seen a lot of that, the ongoing projects or the initiative related to the innovations or the management of waste, but not much on the empowerment. So that we like to empower the human resources in the region, doesn't limit to the Asian countries, but beyond our continents to Africa, to the other continent as well. So we can bring this into the program and the projects. So these projects or the curriculum development projects, we train the new generation of the environmental leaders that help combating the marine plastics, and then we try to equip them with the advanced technologies and management practices OPTOCE would be one of the very good showcase or the case studies that will contribute a lot to the curriculum, to the contents in the program itself. And our program, of course, we would wish to contribute to the 4 SDG 14, 11, 12, and 17, especially on that life below water, that the marine pollutions, together with that sustainable city and community, responsible consumption and production. And of course, we would not wish to do just only for that water pollution or the responsible consumption, but we would like to partner with the other stakeholders in the program so that we can move toward the sustainability of the program. And this program, the master program, we try to create the special features like individual coaching, creative working space, field exposure, and the telemed guidance for each individual students. And of course, it would be prepared in a way that the e-learning courses, e-learning modules also will be as a product of this program. And also we try to showcase the good example from Japan that bring the student from AIT to Japan to witness what are the best practice of the technologies of the management, like the zero waste village in Japan. Then the student should be experienced and exposed to such ongoing activities. But unfortunately, the past year, we could not make a student to Japan because of that pandemic, so that we may be possible to arrange this year, by the end of this year, for the second batch of the students, if they are lucky enough with the vaccine, with the restriction travels to Japan would be less. So our 1-year program, it is contained with that 30 credits, which is the 1 credits in our basis. It is about that 15 study hours, which including the torch parts and the research parts. Then we have offering about that the 12 modules. Each individual modules would be different credits. Some would be 1 or 2 or 3, depends. And of course, with that intensive winter summer program as well. And this is not that full-fledged master degree program as the others, as a normal one. In AIT, normally, it will take about 20 months to complete the master program, but this one is only 12 months. That's been 1 year time. So the research part will take only about 6 credits for the individual research study that will not be a comprehensive thesis research like the others. So that would be the program and in master program. Then the modules, as I earlier mentioned to you, that we have 12 modules, and these combined with the variety of the technologies or the management or the analysis parts. So that AIT, we have developed the environmental engineering and management for almost 60 years. We try to capitalize of our expertise in the solid waste management and then make use of that understanding or the expertise, address the issues of the plastic pollution. And of course, we have to invite the other expertise like marine ecosystem and also the emerging pollution in the marine ecosystem. So we invite the specialized faculty members from our colleagues from other partner university to contribute in developing this kind of a spatial modules or the other modules as well, and like stakeholders or finance and leaderships. So that would be the things. Then our program is not that for only the science or the engineering program, but it is to be more on the interdisciplinary program that we try to train the student to make use of this kind of knowledge and then bring it out to that business models. So instead of that learning how to manage the pollution, we try to encourage the students that from their research, from their interest, how they can develop the business model. So we invite the faculty member from the School of Management in a partner university to think about that after knowing about the plastic pollution control management and the value chains, how they can create the business model. So this is our program that offer. Then as there is a study that could combine with the research, individual research study, that variety of these kind of topics that the first batch students that they are doing right now, they started the programs last year in August, and then in this month and starting from last month to this month, they are doing the research study within this kind of area. But of course, we are not limited to these areas. It would be coming up from the regional projects or the individual interest, because some students, they coming from the government sectors, they're also having a certain issue that they would like to do more research and then use those kind of a study to bring back to their home country or to their own office. Some having the business in the kind of a junk shop in Thailand, and then they starting to do the more research that, well, if they would like to invest into the non-recyclable plastics, how to do that. That would be their research area. So this would be a kind of flexibility that we can entertain the student with this kind of research with our faculty members or invited experts like Dr. Kale and the others. Then just to report to you a bit that for the first batch, we can recruit about 39 students with the full scholarships from the Japanese government. It is quite interesting that we are one of the very first program in AT offering the one-year program. Then we have a variety of the interests from many countries, not only from Asia, even from the Latin America, from Africa, there could be many. So with that, for the first batch, because of the COVID that started last year, then we thought that if to recruit the student from Africa, from Latin America, it could be more difficult to travel at that time. Then we think that at the first batch, we should recruit only the student from Southeast Asia so that we can get the 7 countries. And the first batch, they completed the study visit and also now doing the secret research study. And then next month, they should be graduate after finishing the 6 credits research study. That would be the first batch. The second batch also quite interesting that much more applicants from 44 countries worldwide that they interest. Interestingly, that you can notice there, the highest is the Pakistan, that the country having a lot of interest to do this master program. And then with certain limitation for their travel or for many other interesting challenge, we can recruit for this second batch, January this year intake. You can get about 29 students from 14 countries. So, but anyway, we still can get from South Asia, from Africa as well, that you can notice there, the Cameroon, Ghana, Morocco, Uganda, that they can. And interestingly, that you notice there, the Nepal and Bhutan, even if they are the landlocked countries, they still interest in the marine plastic pollutions. That, of course, even the landlocked country, I think they should be the one that contribute as well, because they should also release the plastic pollution to the rivers, not connect to the ocean directly, but pass through India or Bangladesh, and then they end up into the ocean anyway. So that is the second batch. Then just to brief you with these video clips of our activity in the past, that to share with you a bit, if you can see the video. You hear the sound?
Yes.
Apart from the in-class study, we also bring them out to expose to the many activities. Okay, I think that's about the 2 batches students that have done in the past. But recently, we are also recruiting the new intake in this coming August that we hopefully will get about 40 plus students to be recruited. And now today we get about 130 plus applicants from 28 countries. Nigeria, Bangladesh, Ghana, all over the developing countries that we can offer the scholarships, but I don't know how many that they can manage and arrange themselves to be AT in Thailand very soon. So the curriculum we developed not just used by AAT itself, but we commit to the Japanese government that we would wish to transfer to the others as well. Like now we having a certain collaboration that developed an MOU with the Ramkhamhaeng University, Ubon Ratchathani Ratchapat University that signing the MOU that they wish to take our modules. Some like Ubon Ratchathani Ratchapat University, they may have no master program yet in this area. Then they may like to adapt that into the undergrad program. That's also possible. And then we also having ongoing collaboration with Kasetsat University, Thammasat University, Satsin School of Management, and King Mongkut University that they may like to take part of our modules to be there. And interestingly, we try to approach to another private school, so-called the Merchant Marine Training Centers that they carry the big boats, the big ships all over the area, the countries that they're training captains or others that selling the boat. And then we discussed with them that, well, within the boat, they also may generate a lots of that, the plastic waste into the ocean as well. Recently, the case in Sri Lanka, you may have heard about that after the fire on the boat or the ships, it caused a lot of that marine pollution. So that they may interest to take up as part of our modules into the program. That also possible. Regionally, we also try to work with in the regional projects like the Maldives Enhancing Employability and Resilience of Youth Development and Delivery of West to Well course, which is sponsored by the World Bank. So we would like to take them into our program and then train them that if they interest into the waste to well, what about the plastic waste? Then the Maldives University don't have the master degree level yet, so that we can train the faculty members there to use our modules into the undergrad program or the vocational study levels or the college up there in Maldives. In Bangladesh, we also try to approach to the University Grant Commission that also having the possible sponsor by the World Bank that they would like to take the modules into the university program, either the private or the national or the private university. Then later we may like to explore the possible collaboration with CMO, Southeast Asia Ministry of the Education Organization that they may wish to accept our modules, and of course India, Sri Lanka would be a possibility that we can transfer up, and of course our partners here in OPTOCE program. If you're interested, we can discuss further that whether you would like to get our curriculum, and then we can talk about that, how to do and what to do with the program. Okay, that's all for introduction. That just like to share with you the activities and also the ongoing work. And then, of course, it would be more interesting that we still try to collaborate with many other programs or the regional projects that we can sustain this kind of program in the region in AAT. Thank you very much.
Thank you, Dr. Thammarat. That was very interesting. You almost make me want to go back to studying by watching this.
You should be the lecturers here, Anneli.
Yes. Okay. Thank you. Now we are closing in to the very end of the webinar. And the only thing that is left for me to do is give the word to my dear colleague, Kåre Helge, who will give the final remarks of this webinar.
Thank you, Anneli. I really have to say that I am impressed. All the achievements we have seen during this half-day seminar and what you have been able to do, even despite pandemic restrictions. So then we can actually ask the question, what will you be able to do when we are back to normal? I like to see, and I'm really looking forward to be back to normal together with you and go along with you on the next journey together without this pandemic situation. Anyhow, I think what you have shown us is very comprehensive. It has also been very complementary. As you might know, we will continue this project for another 2.5 years at least. So we might be willing to discuss with you other and further studies that we need to take up. So we will need to have a dialogue about this. I think we all have, facing the same challenges. We are facing, global warming, and the world needs to reach net zero by 2050. We are in the 6th mass, elimination of biodiversity, which we really need to deal with. And we also have seen in the presentations earlier that if we don't do anything with microplastic, we will actually have more plastic in the ocean than fish. So we have a lot of challenges which we need to work on together. And I think this forum today really shows that 5 countries, okay, I'm very sorry to see that Myanmar could not attend this meeting due to obvious reasons. But apart from that, we have 4 major Asian countries which are coming together, collaborating, and really do things together. And this is very encouraging for me. So at the end, I would like to thank you for all your contributions. I'm, as Anneli said in the opening, the next forum will be presenting, the final research and maybe even disclose some new research activities between us. But again, thank you very much for your contributions, and I wish you all the luck. And I hope that you will be having the jab very soon, and that we all will be hugging each other in the near future. Thank you very much for your contribution, and stay safe.
Okay, thank you.
very
Thank
much.
you all.
How about a group photograph or somebody?
Yeah, we can take
Oh,
a photo. I agree. That's a good idea.
Yes.
Yeah.
If everyone can turn on the
Open your
camera.
camera.
Southern looks very smart, so I want you change your hairstyle. So let's have a group photo.
Wonderful.
Who is good in that?
I can do it.
See,
Everyone
not only
ready?
me, everybody is interested. Everybody open the camera.
Yes, everyone.
Yes.
Please.
Yeah, good.
We'll give you a few more seconds to open the cameras.
Okay.
Ready?
Great.
And we have a photo.
Thank you.
Oh, great.
Thank you.
Thank you all.
Very good. Okay. Thank you.
Very
Thank
good.
you. Bye-bye.
Bye-bye,
See you again.
everyone.
Bye-bye.
Bye-bye.
Good
Yeah,
night.
bye-bye.
See you in Icon
Bye.
SWM.
See you soon. Thank you very
Yes.
much.
Okay. See you. Thank you.
Thank you.